Welcome back. Theorem. If S equals V1 through Vn is a basis for a vector space V and T equals W1 through WR is a linearly independent set of vectors in V, then R is less equals N. This is a very important result. What it says is, if you have a basis with n vectors, then every linearly independent set of vectors will have fewer vectors than n. That is, a linearly independent set is always smaller or equal to the size of the basis. Proof. Start with your basis. Add one vector from your linearly independent set W1. Call that T1. Notice, my original set S spanned V. So, if a set spans V, then a bigger set automatically spans V. So, T1 also spans V. Now, if W1, you know that W1 comes from V. It is living in T, but it also comes from V. Everybody comes from V. V is this vector space. Since S spans V, W1 has to be a linear combination of V1 through Vn. In other words, T1 is linearly independent. Linearly dependent. If one vector is a linear combination of the others, then it is linearly dependent. Therefore, there must be some vector starting from the second position, that is from here until here, that is a linear combination of the previous sets. So there is a vector Vj which is a linear combination of the preceding vectors of T. Moreover, you can drop it. If you drop it, you get a new set which also spans V. Okay, span of S1 is also V. Now, take this S1. So notice what we did to S. To S, first we added W1, and then because of dependence, we dropped some Vj. Now we are adding W2 to S1, and we are checking for its linear dependence. It will be again linearly dependent. So there is some other vector in T2 that is a linear combination of the preceding vectors. What does that mean? Somebody from here, it cannot be W1 because you see W1, W2, they are linearly independent. So W1 cannot be dependent on W2. But somebody from the rest of the V's will be dependent on the previous ones. Okay. Exactly what I explained. Since my original T is linearly independent, W1 and W2 are independent. They cannot depend on each other. So there must be some other vector, let's call it Vk, who is dependent on the previous ones, and we can drop it. Call it S2, where S2 spans the entire vector space V. We keep repeating this process until and again until we run out of W's. You see, W's were the T's. You can keep adding to S and dropping a V. Keep adding to S. We can keep doing this until we run out of W's. In other words, there has to be fewer W's than V's. Okay, so number of W's should be less than number of V's. There, that is, R has to be less than N. Okay, why can we keep doing this? Because we want to make sure we keep spanning V. All right, so if we want to continue to span V, then the W's we have to run out of them. All right. This proves any linearly independent set has fewer elements than any basis. This is a very important story because this is very, very important. Suppose S, V1 through Vn, and T, W1 to Wm are two bases, two different bases. Then the number of vectors in S and the number of vectors in T must be equal. What does this say? Any two bases of a fixed vector space should have the same number of vectors. Since S and T are bases, they are both linearly independent. So we are going to use the theorem we just proved. First, think of S as a basis, T as linearly independent set. Then linearly independent set have fewer vectors than the basis. So M is less equals N. Similarly, now think of T as the basis and S as the linearly independent set. Linearly independent set have fewer number of elements than the basis. So N, that is the linearly independent set, has fewer elements than M, that is a basis. In other words, notice M less equals N and N less equals M. The only way this can happen is when M is equal N. What's the remark here? If a vector space has a finite basis, then every basis of V is of the same cardinality. What does the word cardinality mean? It means number of elements in the set. So number of things in your set has to be the same. So exactly what we said. If you have two different bases, then they should have the same number of vectors or same number of elements or same cardinality. Cardinality means number of elements. S has cardinality N, T has cardinality M. If they are bases, both bases of the same vector space V, then N has to be equal M. A vector can have different bases, but they all must have the same cardinality. Here is an example. The vector space R2. R super 2 stands for column space. It has standard basis 1, 0, 0, 1. Remember standard basis or natural basis? It's with EIs. Okay. In this case, it's only two-dimensional, so 1, 0, 0, 1. Now, the same R2 also has bases 1, 1, 2, 1. Okay. We have to check the claim. Is B2 also a basis? Well, let's check whether it is linearly independent. Suppose A times 1, 1 plus B times 2, 1 is the 0 vector. Then A plus 2B is 0. A plus B is 0. You have two equations. A plus 2B is 0. A plus B is 0. From the second equation, I see that B has to be negative A. I plug that in the first equation. A plus 2 negative A is 0. Negative A is 0. That is A is 0. If A is 0, B has to be 0. So what did we say? A linear combination of these two vectors is the 0 vector, results in the coefficients being 0 as the only solution. So B2 is linearly independent. Remember, to be a basis, you want to be linearly independent and be a spanning set. So consider span of B2. Is it equal R2? Let's take any vector from R2. We want to check whether this vector is in the span of B2. Let AB equals x1 times first vector plus x2 times the second vector. So x1 plus 2x2 is A. x1 plus x2 is B. Augmented matrix 1, 2, 1, 1, AB. We want to use elementary row operations. So let's see. I want to get a 0 here. So negative row 1 plus row 2 is the new row 2. Negative row 1 plus row 2 is the new row 2. I got a 0 here. Now I have a negative 1 and negative A plus B. So I need to multiply row 2 by negative 1. That gets me a 1 here, and this becomes A minus B. What does this say? This immediately tells me x2 has to be A minus B. And the first row gives me x1 plus 2x2 is A. I already know what x2 is, so we can solve for x1. Just substitute x2 equals A minus B. Simplifying, I get 2b minus a to be x1. In other words, we are able to solve for x1 and x2. Therefore, span of B2 is R2. So, B2 is also a basis. So, let's go back. You see, that's a standard basis. This is a non-standard basis. But what's common between them? Two vectors, two vectors. That is, the cardinality of every basis has to be the same. Okay. So, there are infinitely many bases for R2. The natural basis B1 is intuitive to understand. What is dimension? So we have now shown that every basis must have the same number of vectors. We have seen that every basis of a vector space has the same number of vectors. That number, so the dimension of a non-zero vector space V is the number of vectors in a basis. So we know that every basis will have the same number of vectors. That number is called dimension. Notice we are talking about a non-zero vector space. What happens when your vector space is just the zero vector space? That is, set containing one vector, zero vector. Its dimension by convention is zero. Okay. A vector space that does not have a finite basis is said to be of infinite dimension. We denote the dimension of vector space V by just writing dim of V. Dim is a standard notation meant to use dimension. Corollary. If the vector space V has dimension n, then a maximal independent subset of vectors contains n vectors. Let S be V1 through Vk be a maximal independent subset. So you see what we are saying. Look at all linearly independent subsets of V. Look for that one which has the maximum number of elements. So, if span of S, so you already know it's linearly independent. How do we know it is basis? Well, we have to check its span. What if its span is not all of V? Then there is a vector in V, which is not in the span because V is bigger. There is somebody who is not being hit by S. So throw that V in a new set S1. Take your original S, add that new vector. This has to be linearly independent. Why? Because the first K were linearly independent and V was not in the span of this. That is, V is not dependent on the previous ones either. This contradicts the assumption that X is a maximal independent subset. You see, S is a maximal independent subset was our assumption. That is, no bigger set can be linearly independent. Therefore, we hit a contradiction, which means this assumption span S not equals V is false. In other words, span S must be V. Okay. Therefore, S is not only linearly independent, it also spans V. So it is a basis. So this is a very important result. Maximal independent subset. Maximal independent subset has to be basis. If a vector space V has dimension n, then a minimal spanning set contains n vectors. We'll come to this corollary in our next video.